principle of conservation of energy, means we have to say loss in potential energy is equal to gain in kinetic energy of translation plus rotation, and gain in potential energy equal to loss in kinetic energy of translation plus rotation. In this case, the principle of conservation of energy applied for the conservative plane as well as non-conservative plane. Generally, in conservative plane, no torque takes place, means this application is used for the non-conservative plane, that is rough inclined plane. Now, angular momentum. Moment of linear momentum is called angular momentum, that is L is equal to R cross P, means the direction of angular momentum is perpendicular to the plane containing R and P. L is equal to RP sin phi, or L is equal to R sin phi into P, or we have to say perpendicular distance into linear momentum. If phi is equal to 90 degree, L is equal to R into P. L is also given as mv into R, or L is equal to I into omega. These are the various forms of the angular momentum. L is also given by L is equal to 2m dA by dt, where dA by dt is called aerial velocity, means the swept area per unit time, or it is defined as area sweeping by a body in a given time. Relation between the torque and angular momentum. External torque applied on a body is equal to dl by dt, or rate of change of angular momentum. In this case, the proportionality constant is 1, means we have write torque is equal to dl by dt. If no torque applied on a body, that is dl by dt is equal to 0, means L is equal to constant. For L is equal to constant, we write I into omega is equal to constant. That is I1 omega 1 is equal to I2 omega 2. A simple example in which we have to apply the principle of conservation of angular momentum, because for L is equal to constant, which is initial angular momentum is equal to final angular momentum, it is also called principle of conservation of angular momentum. We consider a simple example. Two disks of inertia I1 and I2 having the angular velocity omega 1 and omega 2 kept at one another gently. Find the common velocity and loss in kinetic energy. Apply the principle of conservation of angular momentum. Means initial angular momentum is equal to final angular momentum. Initially, the angular momentum is I1 omega 1 plus I2 omega 2, and finally it is I1 plus I2 into omega, where omega is a common angular velocity. Means we have to write I1 omega 1 plus I2 omega 2 is equal to I1 plus I2 into omega, and omega is given by I1 omega 1 plus I2 omega 2 upon I1 plus I2. Loss in kinetic energy is determined by initial kinetic energy minus final kinetic energy, and this is given by half I1 I2 upon I1 plus I2 into omega 1 minus omega 2 whole square. Again, we just consider few applications of principle of conservation of angular momentum. Case 1. For L is equal to constant, that is if no torque is applied, dm by dt or 2m dA by dt is equal to constant. That is dA by dt is equal to constant, means aerial velocity of a body is constant. This equation is generally used for the Kepler's second law, in which if no torque applied on a body, then planet swept equal area in equal interval time. This is called angular momentum is constant, and aerial velocity of a planet, that's why aerial velocity of planet is constant. Case 2. For L is equal to constant. In case of Earth, I is moment of inertia of Earth, which is given by 2 by 5 mr square, and omega is angular velocity of a Earth. That is I into omega is equal to constant, or 2 by 5 mr square 2 pi by t is equal to constant. R square upon t is equal to constant. T is proportional to R square. That is T2 upon T1 is equal to R2 upon R1 whole square. This equation is generally used to determine the time period of the Earth if the radius of Earth changes. For example, if the radius of Earth becomes half, then time period of the Earth becomes 4 times, and vice versa. If radius of Earth reduces to half, then time period of a Earth is also reduces to 1 by 4 times.